Good afternoon, this is Schweitzer, and we're going to do a little video here on some answers to some oxidation reduction reactions. Again, this is not a ton of information about how it's all working, a little bit here and there, but just the answers. Alright, so in this situation, I'm going to do a couple of examples here. But in this sense, metals will exchange with metals. So in this case, I have a metal here which is zero charge. This is a plus 3. This is my spectator ion right here. It's asked me to circle that. Alright, and therefore, again, as we exchange electrons, we exchange charge. These particular atoms have very specific charges that they can attain. Aluminum only has the option to go to plus 3 or 0. And the sodium can go plus 1 or 0. So NaC2H3O2. And this is a plus 1 and a minus 1, which is why it's written the way it is. Alright, next thing we'll do is we'll look at the half reactions. So who's involved in this exchange? The aluminum goes from plus 3 to 0, and the sodium goes from 0 to plus 1. So there's an exchange of electrons. I have aluminum going from plus 3, and the aluminum metal goes to 0. We have the sodium going to 0, and the sodium plus is Na plus. There you go. So this is what happens over the course of the reaction. The aluminum goes from 0 to plus 3. It looks like the aluminum here is going to gain 3 electrons. Now again, a positive 3 and minus 3 equals 0. So that's correct. I want the two sides not just to equal 0, but to be equal. Here, plus 1 electron. Plus 1, minus 1 plus 1 equals 0. So this guy is being reduced. This guy here is being oxidized. Alright, next thing we do is we look up our voltages. Actually, let's balance it first. Alright, because this guy has to gain 3 electrons, the only way it gets it from is from the sodium. Sodium can only give away 1 electron. So this thing has to happen 3 times in order to get enough electrons to feed the aluminum. So this guy is going to be times 3, giving me 3, 3, and 3. Alright, now that means my overall balanced reaction, if it happens to work here, which is going to be aluminum plus 3 sodiums yields aluminum metal plus 3 Na plus. Now again, this is all on paper. So we have this thing in our exchange, we got to check to make sure it runs. And again, not everything is going to run just because it runs on paper. So we call these voltages as how well an atom wants to take part in a process. Positive means yes, negative means no. So what we do here is now this is the oxidation, this is the reduction. So we need to look up at the reaction, what's called the reduction potential, and see what the voltage potential is for this process, each half. So the aluminum grabbing 3 electrons, and that's a reduction. It's called a reductions chart. And we're looking for this thing. It is located right there. Alright, so right where is the aluminum? It is located there. It is. Now, the aluminum is gaining 3 electrons to form aluminum solid is negative 1.66. And that is exactly what's happening here. A negative 1.66. The reduction will always be on the chart as is, and you leave it as is. But the oxidation, that's backwards. We won't find the oxidation for this one on here. We'll only find the reduction, and that's at the other side here. Where is it? There it is. All right. And just saw it. There it is. So this is backwards. I mean, electron isn't on the left side, it's on the right side. That's oxidation. So rather than being negative 2.71, I want the reverse of the reaction. It's positive 2.71. All right, this is going to be a positive 2.71. Now, the level of the positive doesn't mean as much for us right now. But you add those together, and again, we're looking at about 1.05 volts, I believe, positive. It just means that yes, it's going to run, And sometimes I use a smiley face just to kind of, smiley face, there we go, just to kind of make a human side of this. All right, and I think that one is pretty much done. This one here, the tin, I'm not going to do the whole thing. I'm just going to mention a couple things about it. Again, tin's a metal. Now, tin has multiple charges. So tin could be 0 charge, which it is right now. There's no charge listed, so it's 0. It could be +2, or it can be +4. Metals cannot be negative. So in this case, we get to pick, because we don't know. The only way to really know would be to physically do it in lab. So Sn +2 is what I'm going to take, and the iodide is going to be the spectator ion, and then the silver will be all by itself with no charge. Okay, so that's that. This is one half, and this is the other half. Okay, the rest of it I'm leaving for you to try and do on your own. All right, I'm going to do one last example here. Set you up here would be number 6. This is one that has a non-metal involved. So the non-metal will exchange with the non-metal. So it's going to be, in this case, this sodium will be the spectator, and I'll get F2 because it's diatomic, they're exchanging electrons, and the NaI will be the other charge. This one's a +1, this is a -1, and there would be 2 of them here because of the fact that I have 2 iodines there. So let's take a quick moment and let's write out the oxidation half reactions. The fluoride negative is going to F2, and there are 2 of them. And I have the iodine, which is no charge, going to the iodine, 2 of them, I negative. All right, and now we add electrons to make sure we're balanced. Now again, these are not going to balance to 0, but they got to balance to each side. So this is going to have 2 electrons. And of course, I add my 2 there because the fluorines aren't equal. And then I have to add 2 electrons right here to make sure these 2 are equal. And this is my oxidation, and this is my reduction. Let's take a moment and check out our reduction potentials. Now again, the reduction chart one will be right on the chart. Nothing needed. So find fluorine, and it says for reduction it's -2.87. It's the very top one. All right, so this is going to be a well, hold on. Let's find the iodine. Iodine's reduction. So a little bit farther down, iodine being reduced is a +0.53. Okay, so this one is a +0.53. Now the fluorine's being oxidized, so that one's backwards, and I have to flip that one. You'll see here, you may have noticed that the original reduction potential is a +2.87. So when I flip it, it's going to become a -2.87. -2.87. Now when you add these 2 together, you get about a -2.3. Because that's a negative voltage, this reaction will not be running. Now, that doesn't mean it can't run. It just means that you need to power it with energy to make it run. It doesn't run towards products all on its own. However, if you did in fact have these as reactants, they would go this way on their own. So the reverse has a -2.3 volts, but the other reverse reaction actually has a +2.3 volts. So the forward reaction not spontaneous, but the reverse reaction would run just fine. If you happen to have these guys in a beaker, they would flow towards the left. If you happen to have these in a beaker, they're staying there. That's what we have. So either way, so I've done a couple different examples of these. Take a look in your workbook, give them a try.